Our next speaker is a great friend of mine. She uses cross-technology to build hardware that combines experience, science, art, and engineering. Her latest project is a non-rigid airship, and she's bringing together motor controls, power systems, and the venerable ESP8266 for communications. But building something that flies has a lot of gotchas, and she's here to share what she learned along the way so that you can not fall into the same traps. Please welcome to the Hackaday Belgrade stage, Sophie Kravitz.
What? No, I think it's good. Hi, everyone. I'm Sophie Kravitz, and I thought I would do a little bit more of an introduction to myself, and by way of introduction, I wanted to show you 5 sites very quickly that I have up on my phone that are not Facebook. So cobalt is something I'm really interested right now because it's in lithium-ion batteries. And there's a lot of human rights issues around it because people are hand mining it. So right now you can find a lot of articles about cobalt, and I happen to be reading a lot of those articles. This is Battery University. Obviously, I'm really into batteries, and this is one of my favorite sites for many years. There's a lot of different material properties on this site for all different kinds of batteries. Go look at it. It's like a rabbit hole that you can fall into forever. The project I'm going to talk about uses an ESP8266, and this is my first project using the ESP. So I've got a bunch of these sites up on my phone because I don't know what the hell I'm doing, so I'm looking at error codes all the time. This is a song that I like very, very much. It's Janelle Monáe. She's an American singer-songwriter from Kansas, and this video is amazing. It's like crazy cool visuals. She's wearing polka dot lipstick. The dancing is really cool. If you're in a bad mood, I think you should listen to this song and watch the video. And finally, this is the article that got me started in being interested in the project that I'm going to talk about. This is an article that was in Popular Science in 2012. I think I read it in about 2015. Yvonne Masson, who's from the Netherlands. Yvonne, who I might think is here. If you're here, I'd love to meet you. This is a great article. And you know, sometimes you read things that other people do, a DIY project, and you think, oh, someone else figured out how to do that. Maybe I could too. And so that's why I decided to try to figure this out. So the project that I've been working on and off for the past several months, or maybe even longer than I'm going to admit to everybody, is a remote-controlled blimp project. And before I really talk too much about my project, there's a lot of confusion about what a blimp actually is. Sometimes they're called zeppelins, which refers to the shape, the iconic shape of a blimp. And sometimes they're called airships, and airships are semi-rigid vehicles that were used in World War I and World War II to deliver passengers and other supplies around. So the picture that I'm showing here it's sad. It's a famous blimp. It's called the Hindenburg Blimp, and it was filled with hydrogen. At that time, hydrogen was cheaper and easier to get than helium. And this ended in tragedy in 1938, I think, where it exploded. It docked in New Jersey in the United States, exploded, and 36 people were killed. And that ended the airship era. So on a more cheerful note, that's not the kind of blimp I'm going to talk about. My blimp is soft, it's cute, it's round, it's filled with helium, it's not filled with hydrogen. And yeah, it's like basically a balloon with some motors on it. And when I started this project, I thought it would be a lot easier. Like, I actually thought, oh, how hard could it be? I'll throw some motors onto a balloon, have some wireless controls, we'll drive it around the house, and maybe I'll be done in a few weekends. But it actually turns out several months later that making something that flies, something that's controlled wirelessly, and probably the most important thing is making it reliable. Reliability is really freaking hard, and it's taking me a long time to get through this project. So the reason I decided to make a blimp instead of a drone, there are a lot of drone projects, and drones are really cool, but they kind of scare the crap out of me, because they have these fast propellers, and they're sharp, and I thought I would be the person that would be controlling the drone, and the thing would fly at me and cut my head off. And, nobody wants that. But a blimp, blimps they're soft, and basically it's a balloon. So, I could be flying it around in this conference right now and probably not cut anyone's head off. So it's not just a remote-controlled blimp. There's a bigger concept to this, and it's a 4-player indoor obstacle course. And there's a story, and it's of sacrifice, shape-changing, and revenge. The blimps have names. There's 4 of them, because it's a 4-player game, and they're called Poppy, Shrinky, Donna, and LaFloaty. And they live on Proper Popper, which is a fictional planet, and they're on a mission. Like most games, you want to stay alive as long as possible. You want to get more points than all of your other people, your other team players that you're playing against, and you want to not get popped. So they all risk their lives every time they go through a hoop. And so a hoop has a motorized heated pin on it. So it can definitely pop you when you go through. And you can get points if you crash into another blimp, if you hit something on the ceiling. There's a whole variety of things that are in this game that you can win. But that's a very big picture, and you need something to act as an anchor point besides just, I'm going to use the ESP. There needs to be more than that. But I had something really easy to choose. It's the hoop. So I own this hoop. It's in my house. It's a hula hoop. And it's 1 meter in diameter. And the best thing about it is that it doesn't cost extra to fly. It's just under the size where it hits the oversized flight limit and the oversized shipping limit. So I decided to use the hoop. The 1 meter in diameter was my first engineering constraint. So I did need to figure out what size the blimp was going to be, the blimp itself, and so it needs to fit through a 1 meter diameter hoop, so I guess somewhere under that. And a big question was, how was I going to get this blimp? Where would it come from? And what I'm showing here is a friend of mine, Che Wei Wang, his CNC blimp-making machine at a college that he built with his students. And this is a 2.5 by 2.5 meter bed. And I'm standing about as far back as you possibly can to get this picture, because it takes up the whole room. And it's pretty crazy, when you're building blimps and then you just randomly meet someone who's like, oh, hey, I have a machine that builds blimps. So, of course I had to go there, and of course I had to spend several hours or maybe even several days kind of exploring the idea of making my own. And this machine is cool. The way it works, it has 2 layers that you put down 2 layers of plastic, PVC or Mylar, whatever your material is. And the head of the machine, which is there, it goes around the circumference. You send it a 2-dimensional file. It goes around the circumference and cuts. And then you flip the head over, which is, I just think that's such a cool design. You just flip it over, and it goes around the edge and heat seals. But I also kind of have a thing about finishing projects. And if I went down this road of learning to make my own blimp or making my own inflatables, I could see a year later I'd be making some incredible parade floats, but I might not have a blimp that flied. So I decided to buy a blimp. And the most attractive blimp shape that I thought that you could buy looks like the one that's here, and this is actually the blimp that I chose. And they come in a variety of sizes, but the blimp size that I chose fits through the 1 meter diameter hoop, and it's just over a 0.5 meter in diameter. So what's interesting about this project is that I figured out how much the blimp could carry. It's a game, right? So it might have to carry sound, which uses up a lot of power. Might have to carry some lights. Hopefully it's hovering and it's got some light patterns happening. So I needed to know how much weight could it actually carry. And so a gram of helium will give you a gram of lift. And I made that blimp shape into a cylinder, used the cylinder formula, came up with the cubic meters, which turns out 1 cubic meter is 1,000 liters of volumetric helium. And this was a little bit disappointing. So I only have 16 grams that I can lift with. So I'm probably not going to be lifting speakers or cameras. And that's, 2 Sharpies weigh a little bit more than 16 grams. So this was a pretty big constraint. The size part was really easy, but figuring out how to make something electronic that's under 16 grams was a pretty hard problem. So I'm going to talk a little bit about the battery system that was on this blimp. And I don't really have normally a lot of emotional feeling towards electronic components. I mean, who does, really? But I actually really hate JST connectors. Like, really, really hate them. And the JST connector usually comes on the end of a LiPo or a lithium-ion battery. And it's like this white connector that goes into its other side. And I always find myself with pliers, like yanking it out or pulling on the wires so hard that it breaks the battery. And so for that reason, I decided to build the battery charging right into the board rather than outside. So I'm answering a question that a lot of people asked. If you're trying to save weight, why would you have the battery charging and all of its related electronics right on the board? That JST connector, which I freaking hate, that's why. The battery charging circuit it's really straightforward. It uses a microchip part that's very often used for charging a single cell battery. So the cool thing, I don't know if this is commonly done, but I had a problem in my first rev where I'd be charging the battery and all the voltage would go into the rest of the board. I'd wake up in the morning and I'd be like, I don't understand why the battery is not charged. And so I ended up building an inverter into the board in between the battery charging chip and the rest of the voltage supply. And so what happens is when the battery is charging, it sends a 1. It sends an enable signal to the rest of the circuit, which gets inverted, which is a 0, which is off, and then that solved that problem. It is an extra chip, though, and I am trying to keep the weight on this board down. But once I tested that the battery charging circuit was working, I started to lay out what a Blimp's controlled system would look like. And I like to build things in modular ways. And so I had a battery charging system, an inverter, motor drivers were a whole nother system. Power was a pretty big deal. And as I mentioned, I'm using an ESP8266 for both the controller, which is a joystick, and for the blimp itself. So it's 2 ESPs talking to each other. And so I had a really lot of unknowns. 100% unknowns, actually, with the motors themselves, 100% unknowns. And I decided to go with a 4mm diameter motor, a brushed DC motor. I didn't know how much current these motors drew. I didn't know how fast they would need to be to make my blimp fly or steer or hover or anything. And I also didn't know how to buy propellers or how big the propeller would need to be. So after some research, I learned that there are two important numbers on hobby propellers, and they are the diameter and the pitch. And the diameter is related to how much force it takes to move your air vehicle through the air. And the pitch it's much like a screw, like what I'm showing here. It's the twist in the propeller. And you can think of it like you have a little twist in the propeller, and it's the bite that it's taking out of the air. And so the bigger the bite, or the larger the number of the pitch, the faster that propeller will go. And so, I did a ton of research on hobby RC forums about motors and propellers and pitch and all this stuff, and then I went shopping. And I was pretty disappointed because none of this type of motor actually comes with a lot of choices. The propellers come with the motors. They don't come with data sheets, and they don't come with a lot of information beyond voltage and RPMs. You don't get any kV, you get no current draw, nothing. And you can buy a lot of these motors on Alibaba or AliExpress, but I really didn't want to have hundreds of the same or the wrong motor in my shop. Like probably many of you here, I already have hundreds of the wrong part in my shop, and I'm really trying to kick that habit. So I ended up, in the US, it's very easy to buy from Amazon. Shipping is free if you have Amazon Prime, and I chose 11 different motors from a brand called Uxel, and they range between 3 and 4 volts and 15,000 and 40,000 RPMs. So just 11 different types all in between there for testing. And this is Rev 1 of my motor driver board. My first and probably second revs of these board, I separated out the ESP circuit because I needed to have something that I could write software in while I was figuring out all the other stuff. And so this picture just shows all the parts that could be in this blimp thrown together on a scale. And I'm only like 4.2 grams off. So I was pretty psyched. This is, I think, probably my second or third rev. And now I'm only 3 grams off of my target of 16 grams. And I fixed a bunch of stuff. I put the ESP on the board, and also you can see in the center there's a header that I'm using for programming. And somewhere in there, I went to a conference, and I learned about Tag Connect, which is a freaking game changer. Tag Connect is this cable that you just touch onto your board. It's a pogo pin system, and I haven't done a lot of manufacturing in large quantities, so I'd never seen this before. It's a system that you just touch your pins to the board and it sends the program, but you don't need to assemble a board with this extra header, or extra weight in my case. And the header that I was using shaved a whole 2 grams off of the board, so that was pretty awesome. And this was my first flight, and I had a lot of problems, like a really lot of problems. The propellers were spinning. They weren't spinning fast enough. The ESPs lost connection like every 5 seconds. And I was 3 or 4 grams overweight, like in that picture I just showed at 19 grams. It actually meant I needed a lot more balloon to hold it up. So I'd actually been pretty lazy with my 11 motors. I hate to present myself as lazy, but I was super lazy. I just reached into that bag. I pulled out a motor. I didn't even look at how much voltage or RPMs it was, and I tested how much the current draw was. And when I tested it, the current draw was 30 or so milliamps, which turned out to be off by a factor of 10 from the motor that I ended up using. And so I designed both the power system wrong and the motor driver system wrong based on this 30 milliamps. The ESP8266, if anyone's worked with it, it sucks up a lot of power, but it also doesn't run very well if it's under about 3 volts. And so all of my connection problems, which I thought were software for a long time because it was my first ESP project, turned out to be all related to power. And the reason for that was that in my laziness, I chose a voltage regulator, AP2112. And that's the voltage regulator that everybody uses in the Arduino compatible circuits and anything Feather, like probably Teensy uses it. Anything that just plugs into your USB port and you use as kind of a dev board. And that's, I use boards like that all the time and I was like, oh, I'll just use that voltage regulator. But then as soon as I plugged a battery into the board, a battery at full charge, a lithium-ion battery at full charge is 4.2 volts. So using a voltage regulator, there's going to be some drop, meaning that this particular regulator, my lazy choice, actually had a drop of a full volt. So the most that could get to my ESP was 3.2 volts, and then, of course, that dropped pretty rapidly with the motors pulling all the current out of it. And I'd also chosen the wrong motor driver, just because I designed for 30 milliamps, and I chose something. I actually did a little bit of a hack. I chose a fan driver motor because it was cheap. It's not necessarily designed to go in backwards and forwards, but I chose it anyway because it was cheap and it was easy and it was there. And it had a really high voltage saturation, so I wasn't able to get enough current to my motors at all. Had a bunch of other gotchas. Anyone here have a new MacBook Pro with the USB-C ports? I mean, don't even get me started. Anyway, USB-C is a total nightmare. Nothing FTDI works on it. Nothing Arduino compatible will work on it. So I also have a Fluke, and a benchtop power supply. They measured a volt different. Turned out to be my benchtop power supply was broken. And then I also, yeah. So this is kind of where I was. Everyone familiar with the engineering happiness curve? I was pretty much not exactly ready to give up, but I was pretty bummed because I had a board that I'd spent a couple months on. None of it worked, and none of my tools, my measuring tools, were working either. So my redesign brought me right back to the happy point in the engineering happiness curve, because I swapped out the voltage regulator for a buck-boost converter. And if you're not familiar what a buck-boost converter is, it's a device that can bring a voltage down, say from my full battery from 4.2 to 3.3, very important, but it also can bring a voltage back up again. So I have 3 motors on my board, and they suck a lot of power. So this little tiny device created a nice, stable power supply for the ESP, and my connection problems, for that reason, completely went away. And I'm just showing here, from a motor driver standpoint, this is pretty much how they work. They have a logic table, and so it takes 2 GPIO, 2 general purpose I/O pins, and you can give it a low and a high to turn in one direction, or a high and a low to turn in the other direction. It's extremely easy, and you can do kind of the same thing if you're PWMing the motors. Or you can make them both high or both low, and the motor will stop. And some of them have an extra GPIO pin where you can make it slow down, like do a slow start or a slow stop. But these are really easy to use. The process that I use for assembling all of my prototype boards, I have a pancake griddle. I use that for reflow. I once had a toaster, and it's like it gets hot on the top part of the toaster. So you put your board in, and I have a scar here, because I just hit the top and it burned the top. And now it's much safer to use a pancake griddle. It's just put it on a flat surface. And I use a soldering iron for anything that's just like 2 pins, resistors, caps, inductors, or whatever. But on this rev, the buck boost is a QFN, and that stands for quad flat, no leads. And I could go into a rant here, because the leads they're like under the chip. You can't see anything. You can't tell if the pins are matched up to the silk on the board. If your chip is lined up right, you can't tell that either. The pitch can be too small, and if you overlap by some tiny amount, as I did, your chip just might not work. And I'm not super new at soldering, but this particular chip, it usually takes me about 6 tries to get it right. So, anyone who's got good tips about QFN soldering, happy to listen. So even though the board, it required a complete redesign, I got to watch nearly the whole season of a show that I really like while soldering and testing. So that was good. So the controller, the PCB requirement was to be as light as possible, but luckily I didn't have any of those kind of problems with the controller. I could make it pretty big and pretty heavy. And so I designed this in Inventor, and it's 3D printed. So just a little bit about interface control. When I'm designing something that a participant or a user or a game player is going to use, I think it's really important that it doesn't require any instruction. So I'll often think about this by imagining a small child walking up to a device and picking it up, and then usually if it's a button, that's the first thing they'll figure out, is that a button moves. And a joystick is a really good choice also, because it's something you can grab onto and you'll instantly see something happen. Joysticks for adults are also really good choices, because we're used to them in old-style arcades, we're used to them in home game systems, and stick shifts in our cars. And so I think that adults really associate joysticks with speed and direction controls. And so I also wanted to make it pretty and go with the proper popper, otherworldly, curvy theme. So that's what the current final design looks like, but this is a Rev 1. Inside of this controller is an Adafruit Feather, which has an ESP on it and power management. So I didn't do any electronics design on this at all. and the ESP communicates over Wi-Fi. I'm still not exactly sure if that is the right choice. Hopefully I'll have a chance to present this sometime in an auditorium like this and see if we can achieve Wi-Fi communications. But I chose the ESP and to use the Arduino IDE for a really basic reason. You know, there's a really good community around these things. There's no Stack Exchange BS. There's lots of people to talk to about how to make it work. And I thought it would be the fastest and easiest way between not having anything and being done. And so to get two of these to talk to each other, there's only one tutorial, that I found ever how to do this. One of them is in station mode, which turns your ESP into a station to connect to a Wi-Fi network. And the other is the server mode, and it's the IP address that the station connects to. So, and the code is pretty easy. They both have the IP address, and the joystick sends the direction and which GPIO pin to the blimp itself. And so, you know, I did eventually fix all of these problems. The board is underweight, and the hardware is, at this point, mostly done. But I went through an awful lot of revs. And I'll just take this opportunity to say thank you to Osh Park, who helped pay for all of these revs. So this is a little demo. Thanks, that's how I felt too. I was like, wow, it works. I have to say that is one take out of, I don't know, 25, 30 takes. It's the only one that the blimp went through the hoop. I have a, you know, it floats pretty well. There's 6 controls. Up and down works really well. Left and right does not work at all. So that's why I didn't bring it here to demo. But I hope, you know, in the future to bring it to something like this to show off. Like, I think I'm pretty close, but it's not there yet. And I'll just close with, you know, finishing is a really underrated and difficult skill. It's just really hard to finish something. I've documented this project on Hackaday.io. You can find it under my profile, and I hope that you guys will check it out, check out the progress as we go forward. Thank you.